This is part of the Heinz Hagel's series of summer talks about physics at the Aspen Center. If you don't know too much about the Aspen Center for Physics, so within the physics community, of which I'm a part, I'm a physics professor in Canada. Within the physics community, especially in North America, this is a renowned institution. This is a place where hundreds, probably getting close to 1,000 people would come every summer. There are programs running all summer long on kind of the most interesting topics in physics. And people come together basically to talk about ideas with one-on-one with other physicists. There aren't too many talks compared to ordinary conferences. It's recognized that one of the best ways to make progress in physics is just to be in a room with some other physicists and talk to them. A lot of times an idea that can seem really great when you're sitting in your office, you quickly realize the problems with it as soon as you're trying to explain it to a few others. And sometimes kind of magical things happen when you just start bouncing ideas off each other. So this is a place that has been the origin of many incredible ideas in physics over the last decades. So tonight we are going to hear about some of these amazing ideas, and our speaker is Shenker. Steve is one of my mentors. I was a postdoctoral researcher at Stanford University a while ago, early in my career, and Steve was one of the professors there, and I would say many of his contributions to physics have been incredibly influential for me. Actually, the very first paper I read that started my research directions as a graduate student was some famous work of Steve from the 1990s. And so there's a bunch of, Steve has many honors and awards. I've got the list of them here, so I don't forget some of them. He was a MacArthur Fellow, received the Onsager Prize. He's a member of the American Academy of Arts and Sciences and the National Academy of Sciences. And from 1998 to 2009, he was director of the Stanford Institute for Theoretical Physics. That overlapped with the time that I was there. And he's been coming personally to this center for the last 40 years. So he's a person that I think has benefited a lot from this place. So he is, as I mentioned, currently a professor at Stanford. He's been a professor at Chicago and Rutgers in the past. And I think the central area of his recent research has been this project to understand gravitational physics in a quantum mechanical way. Many of you know that Albert Einstein came up with, in some sense, our current best theory of gravitational physics. Probably Steve will mention that. But there are certain situations where we have to go beyond that to really understand physics. And so one of those situations is the physics of black holes. Probably another of those situations is the physics of the Big Bang. And so many people, including myself and Steve and others in our theoretical physics community, have been working for, well, again, decades to try and merge these things, quantum mechanics and gravity. And then the last 15 years, last 20 years, during my career, I think we made incredible progress and realized that gravity and quantum mechanics and other areas of physics like chaos theory are all connected in a kind of an amazing way. So Steve is going to tell us about some of these remarkable connections, and hopefully you'll enjoy that. I'm sure I will.
Well, this is on. Good. Glad to be here. Glad all of you are here. And Glad to be back here after 4 years of pandemic in this place that I've been to so often in my career.
4 years.
What I'm going to try to tell you about today are a few other different areas of physics. Idea of chaos, idea of black holes, and quantum mechanics. These ideas have been around for a while and appear actually to be quite different. In recent years, as Mark mentioned, a lot of connections between these areas have emerged. I'm going to try to paint you a picture of some of these connections. Couldn't think of a better organization than actually to just tell you about each of these topics one by one. And as I tell you about them, I'll try to weave some of the connections together. So in the most boring way possible, let's just start at the beginning. Let's talk about chaos. I think we're going to have to typical Zoom. Gotten as a community pretty good at Zoom for the past few years, so hopefully, yes. Good. Okay, so let's start talking about chaos. I'm going to have to start by telling you what chaos isn't. What chaos isn't is regular motion. Our view of the scientific world probably goes back to Newton and Galileo 500 years ago. And this kind of view of the world, you take basic objects, here the sun and the earth, and then you specify their initial configuration. Put the sun there, and you put the earth there. You give the earth some velocity, and then you let them go, and you evolve them. You actually figure out where they're going to be in the future by following dynamical laws, Newton's laws of motion. What happens, as you know very well, as you solve these equations, the Earth goes around the sun. It goes very regularly, just like clockwork. It is part of clockwork. And the future is very easily predictable. After a year, you know the Earth has come back where it started. 2 years, it comes back again. Extremely regular, extremely predictable. That's what our watch is from. What I want to tell you is that that simple situation is not typical. It's usually hard to predict the future. That's sort of intuitive. I'm going to try to give you a precise notion of it. And sort of a very prosaic example is the game of pool. Mind you, in pool, you start out with this sort of pyramid of pool balls in a triangle on the pool table. Nice. Then you shoot a white cue ball at it, and you watch these balls fly around crazily. It's very hard to predict. You shoot this cue ball exactly where all these other balls are going to go. If you're a very good pool player, you can do it. But an amateur, I'm worse than an amateur, really have no control at all. It's hard to be a good pool player because it's hard to predict the outcome of this process. What lies at the core of that difficulty in predicting pool ball? Here's a figure I stole from an ancient physics textbook. We don't study pool in physics anymore. This is an old book. But here's one of the target pool balls, and here's the cue ball coming in. Suppose the cue ball is offset a little bit from the target by a little amount, shifted by a ½ an inch or something. Then when the target cue ball comes in, it goes down, and the target goes up. And you wait a while, this goes quite far down to one edge of the tool table, this goes to the other. Now you suppose you change things and you move this cue ball up just a little ½ inch, just a little bit. Then you shoot it in and the cue ball goes up, the target goes down. This tiny change, changing by an inch or so, can get magnified to the whole width of the pool table. Small change in the initial impact parameter, that's what we call this distance. It's a large change in the final trajectory. But things are sensitive. In fact, we call this sensitive dependence on initial conditions. That's basically a synonym for what we call strong chaos. And of course, it makes it very hard to predict things, because unless you're a very experienced pool player, it's hard to be that accurate. You shoot the cue ball in. You make a little error, and it just mungs everything up. Well, sort of a well-known example where this kind of thing occurs is in the weather. It's hard to predict the weather. And the kind of slogan, the cartoon that goes along with this is sometimes called the butterfly. Imagine a hurricane, let's say, forming off the coast of Africa, and left to its own devices, it might cross the Atlantic and make landfall in southern Florida. Now, run the movie again. Go back where the hurricane was forming. Suppose some butterfly, some beautiful African butterfly, flies off out of the coast and flaps its wings, disturbing the hurricane as it's being formed a little. The weather is sensitive, very sensitive to initial conditions. Then maybe the hurricane's course is different, and it actually makes landfall in North Carolina. So this little tiny perturbation, the flap of the butterfly's wings, is this huge change in the behavior. This is really a fundamental source of uncertainty, even in this kind of classical physics that doesn't have things like the uncertainty principle of quantum mechanics. And I think, just not having thought about it deeply, that a lot of our experience of uncertainty in everyday life flows from this kind of chaotic, sensitive dependence. Well, that being said, and because of, complex political climate we find ourselves in, I have to add some caveats. Sensitive dependence on initial conditions does not mean nothing is predictable. I point out to you that Aspen especially, the summer is hotter than the winter, even though weather is hard to predict. That's just because in the summer, the Earth is tipped more toward the sun in the northern hemisphere, and so more solar radiation falls on Colorado, more energy in, and that heats things up. Conversely, in the winter, it's tipped away, sun comes in at a glancing angle, there's less intensity of sunlight, there's not as much energy, and things are cooler. Now, predicting exactly when the first snowfall will happen, that's something that's subject to chaotic uncertainty. But this basic pattern that the summer is hotter than the winter, that follows from basic energy balance. That is something that's easy to predict. Similarly, if you dump large amounts of carbon dioxide into the atmosphere, you have this very well-known phenomenon of the greenhouse effect. It traps heat. A lot of carbon dioxide into the atmosphere, the Earth is going to heat up. Chaos has nothing to do with that. It's just this energy balance. If you ask, exactly what month a certain glacier is going to melt because of that, that's subject to chaotic uncertainty. These overall patterns are predictable. So don't take chaos as a license to just throw up your hands and say, I don't know anything about what's happening. Bring your winter coat in the winter. So on. Right, well, in physics, we try to measure things. So we'd like to ask exactly how sensitive are things to initial conditions. Well, imagine that this is, let's say, the cue ball when it's just above that center line. Here's a trajectory of the cue ball when it's below the center line. It's making all these collisions, and in fact, these two trajectories get very far from each other. They diverge exponentially in time. What that means is that there's a doubling phenomenon. Maybe you start out 1 inch apart. After 1 second, they're 2 inches apart. After 2 seconds, they're 4 inches apart. Seconds, 8 inches, and so on, a doubling every second. That's exponential behavior. This builds up fast. You'll remember. After 10 seconds, for instance, these two things will be separated by 85 feet. You won't even be on the same pool table anymore. They'll be across the parking lot of the pool hall. So this enormous amplification underlies the extreme difficulty in predicting. In symbols, you write, say, the distance grows like e raised to power, the time times a constant. This thing is called a Lyapunov exponent. The bigger it is, the shorter the doubling time. So large lambda sub L means trajectories diverge more quickly, stronger chaos. Now, weather is actually pretty complicated. Turns out there's lots of Lyapunov exponents. But as I'm told that one of them, sometimes the dominant one, gives a divergence time, doubling time of around 5 days. And this is the time scale in which you can make reliable predictions. You work really hard, maybe you can do them for 10 days. Making reliable, detailed predictions about exactly where rain is going to fall 6 months ahead of time, the fool's errand. It's just outside of practical. There's another way to sort of measure chaos. It involves this idea of running the movie backwards. I didn't use pool balls here. I used actually atoms of gas in a box. Here's an ordered configuration, let's say like the pyramid of pool ball. Give them a little bit of velocities in different directions, let's say by hitting them with the cue ball. And if you evolve forward in time, that's against this arrow, you start bouncing around crazily and fill up this box. It's like pool balls after you've broken them. And this is actually a picture of what we think gas in a box looks like. It's crazy, chaotic motion of molecules. So after you do that, though, you can imagine reversing time, run the movie backwards. Seen this where a movie where somebody dumps a glass of water on the floor and it splashes all over the place. And then somebody runs the movie backwards and magically all these drops of water reassemble, they end up in the cup. And it's so shocking because it almost never happened. The reason it never happens is if you jiggle one of these molecules or cue balls a little bit, the reassembly is disturbed because of sensitive dependence on initial conditions. And so disturbing this a little bit prevents you from reassembling it into that. As you let this go later and later in time, the amount you can disturb these things and not screw up the reassembly is smaller and smaller. The smaller and smaller amount that goes like e to the minus mvs of L2. But late in times, you can hardly disturb this at all without screwing it up. And that's a reflection of chaotic sensitive dependence on initial. Why phrase things this way? It turns out we can arrange such a fine-tuned situation that we're going to run backwards in a black hole. All right, so now I have to start telling you about the second part of physics of black holes. Putting chaos on the back burner for a second. Let's talk about black holes. Well, these are a striking consequence of our best theory of gravity, Einstein's theory of general relativity. These black holes are kind of distortions of the geometry of space and time. That's what we think gravity is, a theory of the curvature of space and time. And it's kind of a knot in that geometry. Classically, nothing, including light, can leave a black hole. The artist's rendition of a black hole. There are actually real pictures of black holes now that you've probably seen in newspapers. Here's a more boring. This is black because basically stars behind the black hole, light shining, gets absorbed into the black hole and it doesn't come back out. It's the name black hole. Now, black holes are hard to visualize. Basically, time and space get mixed up. It's very hard to draw a picture of it that captures all of it. Physicists have a number of sort of shorthand diagrams that represent various aspects of the way space and time get swirled up. They're confusing. So I've chosen a couple of cartoons that illustrate some of the aspects that we're going to care about. I warn you that each of the pictures I'm going to show you, and actually some of the pictures we use in physics, are misleading in various ways. Because they're so strange, you have to look at them in all different approximate ways. That's part of what it takes to get comfortable with these ideas. Here are a couple of cartoons. You have the black hole as kind of like a balloon. The surface of this balloon is called the event horizon. And once you get inside that surface, you can't get out. And in the center, and here's a distortion of the picture. It's a very bad place called the singularity. If you get near that, you're torn apart and very bad. This is deceptive in some ways. The fact that there's a horizon is a good idea. The fact that the singularity looks like something that's just sitting there is wrong. Here's another sort of much more impressionistic cartoon that gets a little bit of it. Imagine that this whirlpool is kind of what it feels like to be near a black hole. This circle here is the event horizon. Once you fall into this whirlpool, you are inexorably pushed forward. You go down the whirlpool, and at the bottom of the whirlpool is this horrible creature called the singularity. And you get smashed against it. You stay outside the horizon and you exert enormous energy. These are very powerful outboard motors on the boats. You burn enormous amounts of energy. You can stay outside the horizon. The closer you want to get to the horizon, the more energy you have to apply. But if you're careless, you let your boat fall behind the horizon, you're out of luck. No amount of energy can get you out. One basic property, black holes have mass. And the size of this horizon, the size of this ball, grows as you dump mass into a black hole. Here, I guess I've said this already. From just outside the horizon, you can escape using. Well, now we can sort of ask, do black holes display any kind of chaotic behavior? It turns out we can set up one of these fine-tuned initial conditions. But if we run the movie backwards, ends up in a special place. So the special place will be, you take a particle of light, it's called a photon, and we say we want it to be a certain distance away from the black hole. These things are like pieces of the black hole. And what you have to do is you have to imagine that photon, the particle of light, starts out extremely close to the horizon. That's the edge of this black region. It skims along the edge for a long time, stays exponentially close to the horizon, and eventually peels off. So you have to start with this thing very close and give it enormous energy. As the thing peels away, it climbs out of that well in that whirlpool, losing energy, redshifting. This is a blue photon, which has a lot of energy. This is a red photon, which has less. So this is this delicately tuned situation, which you can set up. Now perturb it. Remember, the test of chaos is a tiny perturbation of that delicate situation is going to change it completely. So how do you perturb it? Well, let's just drop a little mass, a tennis ball, to our black hole. So this is a tennis ball. Tennis ball weighs something, not a lot. But if you drop it into a black hole, the black hole gets a little bigger. Its horizon gets bigger. So you can see that this black circle is a little bit bigger than this one. And if this photon was incredibly close, it means that that tiny increase in size swallows the photon. Now the photon's inside the horizon and all is lost. The photon inexorably goes and has to hit the singularity. So this tiny perturbation, dropping a tennis ball into a black hole that weighs as much as the sun does, change course of this photon from nice, comfortably leaving this horribly unpleasant experience. That's sensitive dependence on initial conditions in a very serious way. This just says that. You're trapped behind the horizon. If the time the thing to leave is exponentially long, this is exponentially close, so you need an exponentially small mass. This exponential sensitivity is a signal of Lyapunov behavior. So the way that black holes exhibit is sensitive dependence on initial. Turns out black holes are not just chaotic systems. In a precise sense that I'm not going to be able to explain to you here too well, they're maximally chaotic. And the slogan we use, we say black holes are the fastest scramblers in nature. this context, scrambling or fast scrambling is a synonym for strong chaos. This is nice to know that. The gravitational phenomena I've discussed here, horizons getting bigger when you drop tennis balls into them, particles of light skimming the horizon and eventually leaving. These are things that have been known for many years. They're a feature of the classical theory of Einstein's general relativity. They're not all that new. And so I want to explore with you in the second part of this talk, can we go beyond this and use chaos to learn new things about combining quantum mechanics with gravity, that is, studying quantum gravity. Okay, that brings us to the third kind of physics we need to talk about, which is quantum mechanics. I have to give you the world's shortest course in quantum mechanics. I think it's not the world's shortest, it's a very short. Defining feature of quantum systems. Those are systems that are ruled by the laws of quantum mechanics. And the motion is bounded, like the Earth going around the sun, or an electron going around a proton and a hydrogen atom, where the degrees of freedom fly apart from each other infinitely. That the energies of these systems can only assume discrete values. Energy is quantized. Quantum mechanics, quantized, all are getting at the same idea. And these discrete energy levels correspond to independent quantum states. So here's a list of the discrete energies available to a hydrogen atom, electron whizzing around a proton. I have to tell you that, in physics, most of us live with this all the time. It seems second nature, but it is really strange. In your experience, energy doesn't come in discrete lumps. If you're in a car driving along and you want to give the car more energy, you press on the gas pedal, get it going a little faster. The speedometer is not calibrated into discrete jumps. Okay? It looks like the dial can continuously go the speed you want. It's like the car can have any energy you want. In fact, that's actually not quite true. It really has discrete values, but they're so finely spaced that you'll never notice it. If we look at very small things like atoms, discreteness is quite noticeable. It's a remarkable fact in a hydrogen atom. If you try to give it more energy, you give hydrogen atoms more energy by shining light on them, trying to excite them. You can't give it an energy, let's say, in between these two levels. It's against the rules of quantum mechanics. We think they're our best understanding of the rules of nature. Hydrogen just cannot have this amount of energy. Really shocking. The way the world is. Well, it turns out these quantized energy levels in chaotic systems that obey quantum mechanics follow a rather different pattern than that very orderly pattern in the hydrogen atom. This is a kind of messy figure. It's taken from one of the first papers that had to explain this pattern. So I'll live with it and I'll try to explain it. Here are some energy levels from a system that is not chaotic. And I want to point out some features of it. This is a list of like 50 energies. There's a lot of white space here. Easy for energies to be quite far apart from each other. A lot of white space. Sure. Further, these little carets indicate that there are two energy levels so close that you can't resolve them on this picture. And you'll notice that there are a lot of carets here, maybe a dozen. There's a lot of energy levels that are very close. Well, here's an example of a quantum chaotic system. Turns out it's the energy levels, the nucleus of something called erbium, some element we know nothing about. This is some nucleus. So look at this. First of all, there's less white space. Second, there are fewer carets. It's just like one or two here. And so neighboring energy levels seem to repel. They don't like to be right on top of each other. Chaotic system. It's sometimes called that short-range level repel. The fact that there's lots of white space in these non-chaotic systems would mean if you thought about these energy levels as kind of atoms in a sort of gas, it would need to be easy to compress the gas. You'd have all this white space you could press and fill up with energy level. Here, the energy levels, there's much less spacing. They're harder to compress. So we talk about that as long-range spectral rigidity. These seem to be two hallmarks of the way energy levels in quantum chaotic systems. Here's another example. This is actually a quantum version of a pool table. I think this was done numerically, but you can actually do it experimentally. You can carve a little pool table out using the same kind of microfabrication techniques you used to build microprocessors. A little tiny pool table and stick an electron in it to bounce around crazily and ask, what are its energy levels? They'll look like this. This last one is also quantum chaotic, but it's a math problem. Amazingly displays the same pattern. That we won't talk about. So this complicated thing of chaos gives rise to a simplicity in the energy level pattern. It has these two basic characteristics. So let's try to summarize what that pattern means. It turns out there's a remarkable conjecture of which there is enormous evidence, Quantum chaotic energy levels that have this level repulsion and this spectral rigidity obey what's called random matrix statistics. I'll tell you what that is next couple of slides. And a very important thing is that this is a universal pattern. I think it applies to nuclei, to pool tables, either big or microscopic. I think it applies to complicated molecules, electrons moving in disordered material, and even black holes. That will be where we're headed. But first, I have to tell you what this universal pattern is. For that, we have to get our second lecture about quantum mechanics. Tell you how you find the energy levels in a quantum mechanical system. The dynamical rules of a quantum system, let's say the forces that govern the interaction between molecules in a gas, determine a matrix, that is an array of numbers. Think of this as entries in an Excel spreadsheet. So there's a bunch of numbers determined by very complicated rules involving the fact that atoms attract each other with certain forces, and atoms weigh a certain amount, and complicated. And at the end of the day, you can build this array of numbers. It's a 4x4 array. So it's called the Hamiltonian matrix. And there's a thing you can do to these arrays of numbers, these matrices. A mathematical operation. I didn't look, but I suspect Excel, which is this loaded program, probably has this command if you press it. Diagonalize this spreadsheet. If you diagonalize this matrix, you find a set of 4 numbers called eigenvalues. It's just complicated ways of swirling these numbers around. Those numbers, those eigenvalues, are the energy levels of the system. Out of this 4x4 matrix, you get 4 energy levels. Your systems, you'll have a bigger spreadsheet to deal with. But nonetheless, it's just a straightforward mathematical operation to go from Hamiltonian matrix to energy. Well, quantum chaotic system, we believe, has energy levels that have the pattern corresponding to a much simpler matrix. You don't have to spend all this time thinking about the forces between atoms and how much the individual constituents weigh and so on. All you do is you take and build a matrix, an array, and you go to each entry and you flip a coin. Up heads, you put a +1. Up tails, you put a -1. You build this random matrix, with plus and minus ones, that's dictated by coin flips. And then you push the button that says diagonalize on this. The claim is it spits out a pattern with spectral rigidity and short distance level repulsion. And it seems to be quantitatively patterned at energy levels of chaotic systems. So this is remarkable. All these different kinds of quantum chaotic systems follow the patterns, these very simple kinds of random matrices. Now, these kinds of universal patterns are very interesting because once you understand them, there's a possibility of understanding many different phenomena at the same time. And so this seemed like a good thing to focus on. Just to give you a little bit more depth, here's an example of a system with no interaction. All the white space, levels almost overlapping each other. These are three different kinds of random matrices, responding basically to the way you flip coins and stuff like that. And you can see here, there's much less white space. This is the best one, actually. Very little white space, and the energy levels hardly ever overlap. So this looks very much like the energy levels of a quantum chaos. So these patterns are clearly visible. Where are we going with this? Well, black holes in quantum gravity, that is gravity that should obey the laws of quantum mechanics. The best example of such a theory is this thing called string theory. We think black holes in string theory are bound systems, the black hole hangs together. They're quantum systems. They should have quantized energy level. Well, further, we think those energy levels should follow the rules of quantum chaos. They should look like random matrices. To help decide what to look for, we have to figure out how many levels we have to focus on. How many energy levels do you have to study to focus on a black hole? See a black hole. Well, in thermal systems like a black hole, a logarithm of the number of energy levels is called the entropy. What does a logarithm mean? Suppose you had 100,000 energy levels. A logarithm is basically the number of zeros you need to write the number. The logarithm 100,000 is 5. The logarithm is good because it's much easier to write 5 than to write out 100,000. Entropy also means the amount of information required to describe a state. Suppose you wrote out something like this in binary. You have a binary digit. Suppose how many bits does it take to store a binary number? It's the number of ones and zeros it takes to write the number. It's the number of bits it takes to describe a state, to describe its label. So you measure information, how easy it is to describe a state by the number of bits it takes. Now we're dealing with quantum systems, so we don't need just ordinary information, we need quantum information. Quantum information is measured in quantum bits, or qubits as they're called. Ordinary bits are a central part of classical computers. The iPhone or my iPhone contains lots of 64-bit words. Quantum computers, as people are learning how to construct them, have to contain quantum bits or qubits. They're basic to store and process it. But then we have to ask, how many qubits do you need to describe a black hole? There's this wonderful rule that was discovered almost 50 years ago by Wittgenstein and Hawking. They compute the entropy of a black hole, the number of qubits you need to describe it. Take the area of the horizon. Remember, the horizon is this balloon. Its area, and then divide it into little cells, very little tiny cells. The cells are triangles. And the size of the triangles are tiny. Their side is of length 10 to the minus 33rd centimeter. It's like a million trillion times smaller than a proton, million trillion times smaller than an atom. I mean, it's really tiny. The idea is you take those tiny triangles, cover your horizon with them, and you count the number of triangles. Hopefully you need 1 qubit for every triangle. 1 qubit per Planck area. This length is often called the Planck length. Well, you can do this for a black hole that weighs as much as the sun. That was a big thing. If it collapsed into a black hole, it would only be 3 kilometers across or so. The entropy of such a thing, the number of those little triangles, is 10 to the 78th. That's 1 followed by 78 zeros. enormous number. You remember, that's the logarithm of it. If you actually want to know the number of energy levels, you take 1 followed by 10 to the 78th zeros. This is like people that think about large numbers. If this were like a Google, this would be like a Google. Okay, these are huge, huge numbers. And so this is an enormous number of energy levels. Black holes are chaotic systems, so the levels should look like the eigenvalues of a very large random matrix. This isn't a 4x4 spreadsheet anymore. This is a 10 to the 10 to the 78th by 10 to the 10 to the 78th spreadsheet. This is big. Now, when quantum mechanics goes away, this discrete set of energy levels goes away, and the energies become continuous. So this discreteness in the random matrix behavior are distinctly quantum gravitational phenomena. So they are something very interesting to study if we want to learn how quantum mechanics and gravity interact with each other. Well, it's interesting, but up till recently, these ideas have been extremely difficult to study. Hamiltonian relevant for black holes is complicated. And matrices are very, very large, these 10 to the 10 to the 78th square array. Recently, in the last, I don't know, half a dozen years, a simple toy model of a quantum black hole has been introduced to enable us to make progress in understanding these. Just as a meta remark, I should say that this is a very powerful strategy in science. You can't understand the problem you really are interested in. What a toy version of the problem. If this is too hard, think about checkers. This is too hard, think about glaciers. And then when you understand that, maybe then you can go back up and understand. Look, the practic is, here's this black hole with these qubits in each of these little tiny cells. So what you do is you sort of abstract this and make a model of pure quantum information, that is, pure quantum bits. Just say, you imagine taking some of these bits and hook them up in a rather arbitrary pattern. So each qubit is coupled to 4 others. Take n qubits in groups of 4 with kind of take random coupling. This is called the Sachdev-Kitaev model. It's been a workhorse for us thinking about quantum black holes in the last half a dozen years. The heart of what makes this system simple is it describes a black hole, but not the dimension we live, 3 spatial dimensions and 1 time dimension, but in 1 space dimension and 1 time dimension. And gravity and geometry is much simpler, those dimensions. You know, it's easier to imagine curved things if they're just 2-dimensional, like sheets of paper, rather than curved 3+1 dimensional objects. What kinds of qubits do you use? Well, there's a spirited competition going on to determine the most practical kind of qubit to build quantum computers. Many of you even seen a little bit of this kind of contest that's going on. Startups, companies getting in. One popular kind is what's called superconducting qubits, the little loops of superconductor or flux. Google, there's IBM focusing on this technology. Trapped ions is another, where you take an atomic ion, molecular ion, in a magnetic trap. There's a company called Ion 2 on the East Coast, connected to the University of Maryland, the NSA, that works on this. Another one are things called Majorana fermions. Here, Microsoft is championing this approach to qubit. And for various reasons, the SYK model uses Majorana fermions. That they're simple to handle mathematically. And the idea that ideas from quantum computation feed into building these simple black holes is one example of an emerging synthesis concepts in quantum black hole physics and in the physics of quantum computation. We're actually finding this very surprising interplay where we have a lot to learn from people that are focusing on building quantum computers and the theory of that. they hopefully have a little bit to learn from us who are thinking about gravity and black holes. It's been a very exciting back and forth over the last decade or so. When things like that happen, you feel like you're maybe on the right track. It's like two different groups working hard come to the same kinds of notion. Then you're able to trade experience and trade ideas, and things go much faster. Oh, another thing that makes the SYK model a good model for a black hole is it's maximally chaotic. A black hole has its largest possible Lyapunov. It has a sector that behaves like gravity in one space and one time. I mentioned it. And so hopefully this means that lessons can be learned about quantum gravity. And hopefully, you look at things that are universal enough, generalize to higher dimensions, like the 3 space and 1 time dimension that we live in. Well, for n Majorana fermions, it turns out that you need 2 Majorana fermions to make a qubit. The number of energy levels is 2 to the n over 2. So suppose you have 34 Majorana fermions, you have about 128,000 energy levels. Your spreadsheet is 128,000 by 128,000. That turns out to be at the edge of what you can diagonalize with classical computing. I don't know, half a dozen hours on a very fast. This turns out to be large enough to be interesting, mock up interesting behaviors of black holes. Even though it's a lot less than 10 to the 10 to the 78th. It's big enough. It's not 1, it's 128,000. That's pretty big. And so what we've done is we've actually dug into this system and looked at the behavior of these energies. So here's an example of, I guess, a set of about 50 energy levels for this YK model. You can look at that. Pretty soon you get pretty good at looking at these spectra. There's not a lot of white space here. The energy levels don't look like they're overlapping much. And in fact, this is a pretty nice quantum chaotic spectrum. This toy black hole seems to display attributes, chaotic energy levels. Again, in physics, you care about quantitative tests. So we need a more quantitative test than just eyeballing it and say, yeah, that looks pretty good. The quantitative test we use is actually to study, those of you that are expert, we take the differences of energy levels and we take the Fourier transform. This double sum of these exponentials, differences times time. Don't worry about it. It just gives something the function of something called time. And so then you graph this quantity versus time. And if you try it out on random matrices, find a structure like this. At early times, you have something we've called a slope scoring. It depends on details of the system. Then you find a linearly rising thing called the ramp, then a horizontal thing called the plateau. The ramp is a signature of long-range spectral rigidity, the fact it's hard to compress these energy levels. The plateau, or really the sharp corner, is a signature of short-range energy level repulsion, the fact that the energy levels don't like to be on top of it. So this is the pattern you need to look for. And so we computed this in this SYK model, and there's actual numerical data. And sure enough, you have a nice ramp plateau. And if you look at it more carefully, this quantitatively agrees with the Ray random matrices. This toy black hole seems to have energy levels described by random matrices. It's very plausible that this will happen in higher dimensional black holes as well. They're chaotic, and this amazing universality, this phenomenon as well, is to apply all over them. Well, this kind of phenomenon then should have an explanation, the quantum theory of gravity. Oh, there's a little secret I have to tell you. We don't really know what the full quantum theory of gravity is, so it's a little hard to answer this. But we know lots of pieces of it. And we have to see if we can identify a piece that might explain this. Now I have to give you the world's shortest course in the theory of quantum gravity. I'm sure all of you have heard that another basic aspect of quantum mechanics is the Heisenberg uncertainty principle. It's impossible to measure the position and momentum of a particle at the same time. Measurements interfere with each other. There's no such thing as a particle with a precise position and a precise momentum. Say these quantities are not fixed, they have quantum fluctuations. Quantum mechanics makes these things not certain. The analog of position and momentum in gravity is the geometry of space-time. So in quantum gravity, geometry is not fixed. It has quantum fluctuations. And so what this means to study quantum gravity, we have to study multiple geometries. So the question is, can we find another geometry besides the black hole that might explain some of this random matrix? And in these simple models, simple SYK type inspired models, we've been able to do this. So you include the contribution of multiple geometries, and this ramp region can be explained by a different geometry than that of the original black hole. It looks like this. Call it the double cone. It's a geometry with one space direction and time that goes around like this. I told you these geometries are one space and one time. So this thing, when you calculate its contribution quantities, describes the ramp. So we see that universal random matrix statistic is a feature of quantum chaotic systems explained by other geometries in the theory of quantum gravity, at least in this simple model. So the double cone represents a one-dimensional spatial universe evolving in time. So this one-dimensional world where we live in 3 dimensions, moving in time. People in this world would live on a one-dimensional universe, evolving in time. This thing has another name. It's often called a space-time wormhole. You may have heard about the word wormhole if you go see science fiction movies, Interstellar or Contact. Wormholes come up all over the place. The wormholes of those science fiction things are often like this one-dimensional slice of this thing. This double cone has a natural generalization to higher dimensional black holes, suggesting a mechanism for universality. You just find one of these things in a more complicated model of quantum gravity, and this will explain the same ramp. The plateau I pointed out to you turns out to be more complicated. Basically, you have to study even more complicated geometry to understand it. Well, this is a very nice story, but there is a fly, or a really serious fly in the way. This is fine as far as it goes, but things are actually more complicated. The SYK model we work at doesn't describe just single theory. I told you couple these qubits with random couplings. Put you some other set of random couplings, just as good a model. You really have a whole set of closely related black holes, an ensemble, a quantum black hole. The curve I showed you looked pretty nice and smooth, was the average over a bunch of different closely related models. But in more realistic models of quantum gravity, not ones that look exactly like our world, ones at higher dimensions where we have a lot of confidence that we understand aspects of them, that come from string theory. There's no such ensemble. There's just one kind of quantum gravity. No averaging is allowed. What does this spectral form factor, this diagnostic, look like then? This is the nice average thing. This is what happens when you don't average. Red scatter here. It happens if it takes one theory of quantum gravity. Without averaging, this nice rampant plateau is noisy. Look, you can draw a straight line through this red noise and see the signal you're looking for. But you haven't finished your job. We explain just this average behavior. What explains the noise? You won't really understand quantum gravity till you understand that. Well, These very simple models, this toy SYK model, and I have to be straight with you. Actually, this was even a little hard. You had to build a toy model of this toy model to really be able to analyze. Noise can be traced to another configuration. This is this wormhole on as a character. Turns out it looks like other things, like wormholes that are cut in half. Not very creatively, we call them half wormholes. And the half wormholes are the source of the noise. If you average over lots of theories, these things average away and you're just left with the wormhole. If you don't average, these things are there contributing a noisy background. This nice, smooth, rampant plane. The analog of these objects in more realistic, higher dimensional models is a mystery. And I have to tell you that I don't think we really will understand detailed structure of this noise, more generally, quantum description of black holes, until we understand the gravitational description of each of these individual energy levels. Half wormholes are just a first step in that. These are the kinds of things that, we sit outside in this beautiful place, talking about, discussing, arguing, trying to figure out what these theories are doing. There's no better place to do it. I'm glad to be here to tell you a little bit of this. So thanks very much.
If I have to say, this connection between chaos theory, many people study in the past, and black hole physics, which many people have been studying for a century now, is one of the most exciting things in theoretical physics in the last, 5 to 10 years. And Steve is one of the originators of these ideas. So hopefully you enjoyed seeing some of those. And I think we have time for questions if you want to ask. Yes.
Do you see any connection between or relationship between energy and mass and time and space, and where you can have a permutation of those things being a part of the totality of being? And so for instance, when Hawking discussed Hawking radiation,
Mm-hmm.
and the loss of mass,
Mhm.
and LIGO detected the merger of two black holes. The resulting mass was lower
Mhm.
than contributing masses of the black holes. And it appears as though it is maybe reasonable to assume that the loss of mass was in the form of gravitational waves,
Mhm.
which could be described as time-space in some ways, because you have space and time now being outside of this event horizon.
Mhm.
Therefore, energy could be, part of that situation. And not to dare correct Hawking, but is it possible that radiation, Hawking radiation, could be called gravitational waves, and that some of that mass somehow is something else, could have left that event horizon, weird entanglement thing, or some, or wormholes, or specifically tuned to particles of specific mass.
Now let me
Higgs boson.
let me try to answer that. You raise a lot of interesting ideas there, and so I think in the situation detected by LIGO, there's been this amazing detection of gravitational waves when two black holes get close to each other, attract each other, and they kind of spiral in toward each other, and they kind of collide and merge into each other, or just try to swallow each other. Then they end up in one bigger black hole. In that process, the geometry of space and time is distorted, and you have ripples of space-time, as you say, that carry energy away. Those we think of as kind of classical gravitational waves. It would be like a coherent, like laser source of light where you have lots of photons around. So it looks like a very classical wave. The process that Hawking considered was a quantum process. You put quantum mechanics in black holes, you might emit individual quanta of gravitation. called gravitons, photons, gravitons.
That's why I was saying it would be not the radiation and electromagnetic spectrum, but something, maybe some wave particle duality as a quote gravity, gravity.
Yeah, I think we think that black holes by Hawking's process will emit gravitons. We also think they'll emit other kinds of waves, like electromagnetic radiation, bosons, other things, any other kind of ingredients that are around in the world. Now, it's possible that everything secretly is built out of gravity. String theory goes a little bit in that direction, in which case that would be right. But our current understanding, for instance, in the standard model, is there's gravity plus several other things, electromagnetism, weak force, and the strong force. And in that current understanding, Hawking radiation would spit out all those different kinds of quantum.
But there's only gravity, none of the other things. There's no magnetic field outside of a black hole, from what I understand. No.
Could be.
But there's certainly a preservation of angular momentum. So you see, it would be part of the, well, if there were increasing this with either one of those, there could have been synchrotron radiation coming from that too.
That sometimes happens. There can be an accretion disk can feed a black hole and spin it up or down, and you can emit radiation that way.
Another question?
Do you think information is lost in the deep hole? I mean, the dark hole,
No, in fact, that one of the recent progress that's been made, and many people here, the workshop that we're part of, have contributed to it, is to give even more evidence information is not lost. The way it's recovered is incredibly subtle. It's scrambled in a very strong sense. So for all intents and purposes, the radiation that's emitted from a black hole looks random, but very subtly coded in it, the information you threw back in. It's in some sense a kind of quantum chaos. So it's not like information is lost, but it's hidden very, very well.
holographic, is that part of all that?
Yes, well, the models we study, it's not essential holography, but the models that we study lead us to those conclusions are of that ilk.
Yes, one of you. Yeah.
This is not nearly as erudite a question.
I'm looking forward to it. Not an erudite guy.
In one of your earlier diagrams,
Yes.
pictures that you showed the photons in the advanced horizon.
Yes.
And you said that if it remained at the edge of the event,
Yes.
that it's possible for the photon in one respect to bounce off the black hole or
It sort of it skims along the horizon for a long time and finally leaves. You have to put in the energy to do it. You have to set it up very carefully. It's not natural for that to happen. Like setting up this very special, unusual configuration.
well, spacecraft.
Yeah, you need a spacecraft with incredible rocket engines that could, more powerful than anything we know about.
Anything that's in space that comes into the event horizon is going to wind up at the singularity.
It gets close enough. Yeah, including spacecraft. Good to stay away from them.
I'm trying to visualize the geometry of a
Uh-huh.
black hole.
Uh-huh.
The cartoon showed as a plane, a circling plane, sort of like the end of a vacuum cleaner hose. So I'm trying to
Oh, I see what you mean. Uh-huh.
think of the backside of it.
Uh-huh.
Is it oriented in a galaxy? Galaxy is a certain way, or
Well, sometimes they look kind of on the outside sort of like a star would look. They don't give off any light. So they're just kind of spherical things, and they could have a direction. They sometimes could spin, have an axis. Okay. What's really mysterious though is when you start falling inside them, kind of like what you thought was time sort of changes into space, vice versa. And so it's not like, a star where you know what time is and you know what space is. That's the particularly difficult thing to understand. If you're far away from it, looking at it, it looks kind of like a nice spherical star.
But the singularity would be the center of the sphere.
Yeah, not exactly. No, it's in some sense a singularity. The center of a sphere, you think you could go around it. In fact, when you fall into a black hole is kind of your future. Kind of like a wall you're inevitably going to run into. You get around it. So it's
I'm just trying to think of the other side of it, though.
you mean if you
got the event horizon.
yeah, you can go around it.
Here.
Well, you can go around it, but once you're inside it, then you can't go around anything. Then you're inevitably led to the singularity.
The back there.
In your depiction of the wormhole.
Yeah.
That had a periodic time dimension.
Yes.
Is that interesting at all? Is that like or is that kind of?
It turns out for the applications we're using, that's useful. It's not essential. It's for these particular applications, it turns out having that periodic time variable turns out to be the kind of configuration you want. It's not essential in this wormhole.
Yes.
So you were talking about how, like if you have hydrogen atom, it can only be at specific energy values. And does the energy just, like if you try to get it in between the two, does the energy kind of just bounce off?
This goes through.
It just goes through.
Yeah.
So then how would you get it to the other level? You just have to have enough energy.
Well, so you get up to more, if you give it exactly the right amount of energy, go up to some other level.
Anything else, just
Anything else will go through. In fact, that's when you do what's called spectroscopy. You know, if you shine light through hydrogen, you'll find out that suppose you shine light with all different energies, photons in it. You'll find out that you look at the other side, you'll see certain dark lines corresponding to just the energies that hydrogen could absorb. Almost everything else will go through, but those won't.
the barcodes kind of line up if you had whatever, the spectrographic,
Yeah,
that barcodes, sorry,
Uh-huh.
barcode,
yeah, that's a good analogy.
it lines up with what you would see.
Yes, very, very much so. Yes.
Is there a minimum size to a black hole?
No.
What, a micron, and carry it around with you?
Yeah, I have to do something. Probably not a good idea. I mean, the smallest reasonable black hole is probably something that's of order this Planck size, so really tiny. The thing that you have to worry about with small black holes is that they tend to evaporate, as Hawking taught us. And little black holes carry enormous energy because mass is related to energy. So you're carrying a little one around with you, it might evaporate very quickly, spill all that energy on you, and it will be an unhappy experience. I'm trying to remember, I think a black hole the size of Mount Everest would have lasted from the beginning of the universe till now, would just be evaporating now. Little tiny black holes will evaporate fast.
Can't contain them.
There'll be all kinds of problems. They'll probably be so dense that it would fall right through the earth, things like that. But, so there are many problems with it. On the other hand, we would dearly love to find them.
You could have one as a pet and try to feed it.
You could do that. The cage would be fun. Yeah.
At the back.
You talked about a particle or a photon entering the event horizon.
Yes.
You didn't talk about what happens to time. So if you're an observer,
Huh?
you happen to unfortunately enter the event horizon.
Yes.
Do we know what happens to time as observed by that?
Yeah, it feels when you go through the horizon, if you're unlucky enough to fall in, nothing happens it feels very nice and smooth when you go through the event horizon. We could be falling through a horizon now. We measure the geometry well enough around us, it probably aren't. You wouldn't feel anything. You would just kind of keep falling. And then as you got closer to the singularity, you notice, oh, my legs are getting tugged more weakly than my head, getting stretched out, what are called tidal forces. Then as you get closer to the singularity, you're heading for it. It's kind of in your future. That's where bad things happen.
So that's still gravity and position, but as an observer of time there relative to, let's say, time here.
That's very interesting. It's very time outside a black hole. It's very different than the time inside. So that's part of the confusion in drawing diagrams of black holes. What you thought was time outside, it's like space inside. What you thought was space outside starts looking like time inside. Yeah, well, I understand.
Go ahead.
I have a trivial question. So then, in the classical picture, it looks like event horizon and singularity.
Yeah.
I didn't hear the word singularity at the quantum level. What happened?
Yes, I'll repeat the question. So I talked about the singularity is in the context of classical black holes that Einstein's theory predicts. What happens when you take quantum black holes? What happens to the singularity? This is one of the most important questions in the physics we do. I have to tell you, we know almost nothing about it. Because of my usual poor taste in problems, it's what I'm thinking about right now. And it's very, very difficult. Something bad should happen. We don't know exactly what.
One last question here.
I'm puzzled now because I thought black holes were at the center of galaxies. And every galaxy had a black hole and every black hole had a galaxy, but you're talking about little black holes floating.
There are many more than that. There's big ones that weigh like as much as 1 billion suns in the center of our galaxy or in most galaxies. Like there are lots of little ones. And in fact, this gravitational wave observatory called LIGO is measuring the mergers of black holes that weigh like 10 or 20 solar masses merging with each other. So there's all kinds of them. If you have a certain kind of star that uses up all its fuel, it can collapse naturally into a black hole. They're all over the place and just hard to see.
It's sort of like the black hole, and I mean, like the Big Bang in reverse.
Yes, like the singularity that you hit when you fall in the center. Yeah, it's not exactly like it, but it's closely related. And one of the reasons understand like the singularity, understand nothing about, to try to understand more about the Big Bang. Understand. It might be a place where we can address it with more tools.
Yeah, just one
Sure.
If the galaxies are, if we're expanding, if our galaxy is expanding, which we know from the red shifts,
You mean if the universe is expanding, the galaxy's moving apart? Huh?
then it couldn't be the reverse of the Big Bang, because if it were the reverse of the Big Bang, everything would be coming back together. Everything would be going towards that gravitational pull of the black hole. So the galaxy, our universe must have a lot of energy of its own, stronger than what the black hole is. Is that possible?
There's a couple of threads in what you're asking. The close analogy to the Big Bang is actually when you fall inside the black hole and hit the singularity. It's like a Big Bang in the future. People call it a big crunch. The idea that when the galaxies are spreading apart, that takes energy, that's exactly right. We call that energy that causes galaxies to be spreading apart dark energy. We call it that because we don't know what it is. That's another one of the big mysteries we're trying to.
So maybe in the interest of time, my colleague Steve will.
I'll stick around. I'm happy to stick around.
And anyone that wants to can come up and ask questions, but one thing.
Thank you all for coming. Thanks, Dan.
Evaporate.